Motion of charged particles in electric fields. So I mentioned in the previous lesson that that was the next thing we're going to be doing. So here we are. So we're going to look at two cases. We're going to look at the uniform electric fields case, like we have between parallel plates, because that's a really simple example. So it's kind of tempting to talk about it and apply our uniform acceleration knowledge from previous units. And then the more common case and a little bit more difficult to analyze is when you have non-uniform electric fields, because the force amount and the resulting acceleration changes as the charge moves. So here we go. This uniform field version, we got our charged plates here and so on, right? So positively charged plate, negatively charged plate. We know when they move between parallel plates, we have a uniform electric field. Recall that we have this relationship here, right? Really, that's coming from the potential difference equals the change in energy per charge, right? So we divide both sides by Q. I'm going to start with that equation in a future slide here. We know that the potential difference is the change in energy per charge, right? Rather than just potential. Electric potential is the energy per charge. Potential difference is the change in the energy per charge. And so the change in energy is what we're looking at, right? The change in energy, the change in electric potential energy becomes the kinetic energy. So that's how we're going to get speeds and so on. So that's where we're headed, right? So that's just your potential difference concept rearranged. And so, yeah, we can use this definition, this concept to figure out work done on charged particles. And then, of course, that work done becomes the speed, right? So applications of this, we'll see in the next slides here. Particle accelerators for physics experiments. We can speed up particles, and later on in physics, you'll learn about the idea of how particle physics works, where you smash particles together and see what kind of interactions happen, and that's how they discovered new fundamental subatomic particles like quarks and so on. And the cathode ray tube, old style TVs, and inkjet printers. So the cathode ray tube televisions probably not used very much anymore, but you might see them once in a while places. But how they work is there's electrons that are boiled off from a metal. Back here it's called thermionic emission. You just put a voltage on it and heat it up, and it just gives off electrons. So those electrons are then accelerated through the TV, and they are deflected. So forces are applied onto them through the electromagnetic force that we'll be looking at later. And they get directed. And so they get directed to this spot and to light up a pixel there, and then to this spot, light up a pixel, and they sweep all the way through and light up all the pixels in the exact way needed to make it be the image you need to see at any given second. It's amazing technology, really, for how old it is. They can do that, right? So you've got the electron gun, you've got you got plates that deflect you side to side and up and down, and the beam just gets aimed, and where it lands draws out the picture. Pretty crazy. Inkjet printers are still common today. I think the same as like the Epson EcoTank or any of the ink refillable type printers, not laser printers. So little droplets of ink get thrown through here, and then they get deflected by electric plates. And yeah, there doesn't show it here, but there must be side to side plates as well, so you can direct it up and down, side to side, and so on. So here we go. Here's the mechanics of if you're designing this thing and you wanted to know, trying to figure out what kind of velocity it's going to have and decide, the mechanics of how it's going to work. Here is a question where we have an electron that's initially stationary. It's going to be repelled from a negatively charged plate towards a positively charged plate. So I'm guessing it says the electron started at the plate, basically, because it says away from. That should have been a little bit more clear, but it was at the negative plate, repelled away. Electric potential difference between the plates is 2.40 times 10 to the 2 volts. I underlined that to emphasize the fact that that is a situation where we've got a voltage applied across those parallel plates. So in a previous lesson, I mentioned that there's a subtle difference between a situation like this, where you just have a charge built up, versus this case here, where you have a voltage applied. Okay, so this is the one where the distance between the plates matters, whereas this one does not. And it seems really contradictory, but it's just the way it is. So they're different enough. So given information and all that, and we're of course asked for the kinetic energy, right? Determine the kinetic energy halfway they want specifically. But we're looking for kinetic energy. And so the main concept to think about is the energy concepts involved here, where this thing here isn't obvious because it says delta V, potential difference, but it needs to be obvious that that's to do with energy, right? So potential difference is energy per charge, change in energy per charge, I should say. So the idea is, of course, that change in kinetic energy, so the kinetic energy you end up with, because you didn't start with any, ends up came from the change in the electric potential energy. So rearrange that and multiply it out. You've got your charge times your voltage. We got a kinetic energy of 3.84 times 10 to the negative 17 joules. Done. Okay. Halfway point. So you can actually just say, okay, well, halfway point is going to be half the amount of energy, and that's because the electric force is constant in this type of scenario, right? So we got the uniform electric field stuff, right? So half of that, we get our 1.92 times 10 to the negative 17. Kinetic energy halfway is that amount, okay? If mass is known, you could calculate velocities and so on. We're going to do that soon, okay? All right. With parallel plates, you can even work from scratch, like work with more familiar concepts of force and acceleration and so on, because we know the electric field intensity is the potential difference divided by the space between the plates, right? So if you had the space between the plates, you'd actually be able to calculate out what the actual force is, the actual acceleration, and so on, right? And calculate out, based on uniform acceleration equations. So I'm just mentioning that. We're not doing that right now, because we don't actually have this distance. But I think it's neat to see that we can actually still calculate speeds from the force, even though we don't have the actual distance between the plates. And the reason for that is because as the potential difference across the plates is held constant by a battery, right? We know that's true. So then the amount of energy transferred as the particle crosses between the plates remains constant. So what happens, of course, like we mentioned before, as you're changing the distance between the plates, that just changes the amount of force kind of inversely with the distance between the plates, right? The further apart the plates are, the less force there is. And so overall, that force will do the same amount of work over that entire distance, regardless of what that distance is. So we have remember this thing here is force per charge, right? This is newtons per coulomb, how much force there is on each charge. And so we have the voltage divided by the R, the space between. And then we know that it was, like I said, it's force per charge, right? Newtons per coulomb. So we can put that into Fe over Q. So we can actually get the force, right? Symbolically, anyways, you can get the force, right? It's Q times the 2.4 times 10 to the 2 divided by R, right? So we have that 1.60 times 10 to the negative 19 because it's just an electron, and 602 typically, but I think they're limiting it to 3 significant digits for the textbook question, whatever. And so we have the force in terms of the space between the plates. Well, what's the work done then? Well, work is force times distance, right? So if we want to find out halfway or any fraction of the way, we can just be like R divided by 4 for a quarter of the way, or a full R for all the way across, right? Notice the R's cancel out. So you don't need the actual distance between the plates just to get the amount of energy and the amount of speed, right? Speed, of course, you just go ahead and use EK equals 1/2 mv squared, which we'll do specifically in a slide soon as well. All right. So this is the same example, essentially, right? Just I'll run through it pretty quick because of that, but it does lead to a connection for something we'll see later on, right? It ends up with really fast speeds, and so that's a good lead into a later topic that we'll see in the course. So we have electric potential difference, so voltage across parallel plates in a CRT computer monitor, a cathode ray tube television, essentially. An electron is accelerated from rest of the negative plate to the positive plate. What will the speed of the electron be when it strikes the positive plate? So we know the change in energy is coming from the voltage stuff, right? So we've got that same concept as before. So we get the amount of energy. This blurb here essentially just says, that electric potential energy is transferring to kinetic energy. I should have had deltas in there, but I'm just saying it verbally instead. So yeah, just That's what that blurb is saying. And so really we're just setting those true, right? Setting that to be the case. We get that amount of energy. That's our kinetic energy. And boom, boom, boom. We just solve for V. Okay, so we get our speed. Okay, so that speed, it says here, oh, that's tremendously fast. That's over 10% of the speed of light. And then, so I want to add to that because this is from a previous resource, right? So I would, of course, add to that and say, well, and that's important. So due to the large velocity, being a substantial fraction of the speed of light, there's actually a correction needed in calculating that velocity. And so we'll be looking at that later in the course. Okay, there's some weird stuff that happens when you approach the speed of light, and we'll learn all about it and why it's true. And it's pretty cool that it's quite literally high school level physics, higher end of it, of course, but it's quite understandable. A lot of the things that quantum physics and so on, that's kind of beyond high school level, right, for true full understanding, I suppose. But yeah, special relativity is what we're talking about for this, and it's quite a logical conclusion to a very specific experiment. And so that Einstein discovered it seems like it's a major genius move kind of thing, but really he just accepted what was discovered at the time and thought about the consequences of it. And I'll go through that later in the course for sure. So new question for us here. What's the speed at the middle of the plates? Okay, so we've got this parallel plate kind of situation. Let me go back to the picture here for any one. They're all kind of the same, right? So if we're looking at a halfway point, this one even actually has the halfway point labeled. And we did, of course, do half of that energy. I don't know if I mentioned it at the time. We did half that energy, of course, and then we could get the speed, right? I think it just asked for what the energy is halfway. This approach is a little different and it tempts you to do something wrong. Okay, so if the final speed is 4.2, what's the speed halfway? It's a trick. Watch for that. Like it's a common one to get thrown at you as a question because it's all like so easy to do wrong by accident. So is it just 2.1 times 10 to the 7? Is it just half the speed? The answer is no, it's not. And it's because kinetic energy is related to speed squared. So there's a square root involved, right? So it's not half, it's like based on root 2, I guess. I don't know, but yeah. So how you do this is, of course, kinetic energy is 1 FmV squared, but we know that kinetic energy is going to be half the amount of energy, right? Doesn't mean half the speed, it just means half the amount of energy. So we did that in the previous, we did that here, right? We did that already. But I mean, if you pressed pause and whatnot, and we're thinking about this, a lot of people would have guessed it's just going to be 2.1 times 10 to the 7. And I'm just trying to draw your attention to it. So help you not make that error. Anyway, so yeah, you just have v squared equals some number, right? And so notice we're going to be taking the root of both sides, right? So there's going to be a root of 2 factor in there instead of a divide by 2. Okay, so that gives us 2.96 times 10 to the 7, which of course is more than half of the 4.2. Okay, we've seen this before, right? This isn't specific to electricity stuff. Same thing for a ball falling. If a ball gets a final speed of 10 meters per second as it falls, what speed did it have halfway? Well, it doesn't have just the 5, right? So if you realize that the top half of the journey takes longer than the bottom half of the journey, you don't have as much time to accelerate, right? So it does make sense when you think about it. It's just so easy to make this incorrect kind of assumption. So needs emphasis. Emphasis applied. I hope it is sufficient. Parallel plates resulting in uniform electric fields. Yeah, so therefore uniform acceleration is a special case, of course, as we've been looking at. And so the more common situation is if you have just motion of charged particles in kind of regular electric fields, right? Just fields around a point charge. So if a positive test charge is placed next to a stationary positive field charge, so somehow they lock this one here in place, and then they put one near it that can move, and so on. Remember, this one's the one that's like causing the electric field. This one's just there to feel it. It's not affecting the field. It's a small enough charge in comparison. That's the idea, right? So it'll be repelled, of course, to accelerate away. And then in this non-uniform electric field situation, the net force of repulsion doesn't stay the same, of course, right? It decreases as it goes away. So there we go. According to Coulomb's law, it decreases as the charge distance between the charge increases by inverse square law, and so on, right? So we can still, like, this would be difficult to analyze with force and so on, right? Because everything's changing all the time, but we can still use the energy concepts. That's the trick to be able to do this. And so here we go. We've got these three charges, two charges. Sorry, it looks like three because of the picture, right? But we've got charge A and we've got charge B. And charge B is responding to charge A and repelling away. So we've got a negative charge here and a negative charge there, and it's repelling away. So we want to know the velocity at position 2. So press pause and look through that if you need, but it's at a position of 0.45, and then it repels out to 1 meter, and so on. All right. So when it's next to sphere A, the sphere's energy is all in the form of electric potential energy, right? It doesn't have any initial speed or anything. And so as it repels away, some of that electric potential energy transfers to kinetic, of course, right? And so they're using law of conservation of energy. I'll touch on this in a couple different ways here, but the initial energy equals the final energy, or you can look at it as E equals E prime. The little apostrophe, you call it prime, and that just means final. It's a common notation, so it's good for me to show you all of the different ways that it'll look when you look up information in different textbooks or different questions or different sites that you go to for help or whatever. So the idea, of course, is that the final energy, there's two forms of it, right? So we start all with electric potential energy. We end up with electric potential energy and kinetic energy in the end. So what we have then, if we're putting this all in, we have a KQQ over R and another KQQ over R, and so this is just the initial, and then this is the final, and there's your kinetic energy, right? So if we take away this from both sides, then we have the initial take away the final potential energy, right? Notice that that's initial take away final, which is a little bit uncommon. Normally we think of change as final minus initial, right? So we'll see how this all relates in a second. But yeah, that's initial minus final. But I mean, you just throw in the numbers, you calculate it all out, and you end up with a value for B because we have the mass, we have everything, right? So you just algebra kicks in, calculate out, get your value. Okay, so 170 meters per second, right? There we go. And again, press pause, of course, if you need to slow that down and so on. But yeah, it's an initial minus final situation. Now, the other way you can think about this is, of course, the fact that the energy is transferring out of electric potential, right? And so electric potential energy, the change in electric potential energy, that's a negative, really. It's transferring out and becoming EK. So you can think of it as a negative of a final minus initial, right? Which, of course, is equivalent to an initial minus a final. Right? So the work energy concept, right? The energy transferring out to be kinetic leads to the same result as just pure conservation of energy logic. Okay, so just to reiterate that, the work energy theorem, right, would be like energy transfers into the other form. So this would be like a final minus initial idea, but there's a negative in here, right? So in your conservation of energy idea, what you've got is you've got zero change total, right? And so then you're subtracting the delta E from this side, right? So that's where this, this final minus initial becomes an initial minus a final in the concept. So there's no contradiction there, if you're wondering, right? You just have to watch those negative values to keep things right. So this one's extremely similar. So let you go through that one, but notice that this one, if I didn't show you the clarification and so on, you'd see like this method here, looks a little bit different than this method here, right? So this method here, they thought about it in terms of the conservation of energy, right? And then in this one here, they're looking at it in terms of the work energy theorem, right? The energy transfers from one form to another. Probably should add a delta here too, really. Oh, no, that's just final. That's right. So basically they're saying the final kinetic energy is equal to the change in kinetic energy because it started from zero. And so really what I'd emphasize here is that the change in kinetic energy is equal to the energy that came from, right? That's why it's negative, came from the electric potential energy. So more equal sign right here that would kind of make sense in my mind here for emphasizing logic and so on. Let me just squeeze that sucker in there. I want to make it big for emphasis, but gotta fit, right? So that is your work energy theorem, i.e. energy transfers from form 1 to form 2, right? From electric potential energy to kinetic. That. And yeah, so like I said, if I didn't show the clarification idea or the two different ways, that would throw you for a loop. Like you might think there's two, you have to do it this way or you have to do it that way. I mean, the reality is you can do it either way, right? For the speed, of course, EK equals 1/2 mv squared, boom, 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 do some algebra. The resource where this came from originally started with this, which you don't want to do. That's not an equation you memorize, right? Use the equation that's known for kinetic energy, right? Looks too much like you did it with ChatGPT if you just puke out an equation that no one thinks of as an equation onto a page. Start with the equation that's known and is accepted and used, and use your brain, use your skills to work through the rest. Okay. So the following two questions assume the particle in question is free to move and not experiencing any significant force besides electricity. So in other words, there's no friction, there's no gravity. It's just just talking about the electric stuff. So as a positively charged particle repels from another positively charged particle that is fixed in place, what happens to the net force? What happens to the acceleration? What happens to the speed, and so on? Right. So we've got a positive repelling from another positive. So it's a repulsion situation. So what's happening to the net force as it goes? Well, it's going to get smaller, right? It's going to get farther and farther away. And so it's going to get smaller according to Coulomb's law, KQQ over R squared, right? So as the distance between the plates, or distance to charges, doubles, the force would be less by a factor of 4 and so on, inverse square. What happens to the acceleration? Well, of course, the force is decreasing, the acceleration is going to decrease as well. That's just Newton's second law. What about the speed? Well, the speed is going to be increasing because it's repelling, right? So it's pushing and pushing. It's accelerating less and less, but it's still accelerating. So you could draw the VT graph for that, right? It's accelerating, but less and less. So it'd be put an axis like that, and then you have your VT graph would be a big acceleration at first, and then less and less and less. So a curve like that, if you're following my mouse. Electric potential energy of the moving charge. So what's the electric potential energy of the moving charge? Well, it has lots of electric potential energy at first, and then it is transferring out, right? So it's going to be decreasing. So yeah. So really what's going to happen is, it's in this case, you have a positive electric potential energy, so it's going to a smaller and smaller positive value. Kinetic energy of the moving charge, of course, is increasing, right? I already talked about it's accelerating. So in comparison to an attraction case, okay, so I'll have a summary page coming up that's point out that kind of seems like a contradiction here, but it's really not. So we have a negatively charged particle attracting to a positively charged plate. And so what's the net force on the moving charge, and so on and so on, right? So what happens to, the net force? Well, the net force as you're going closer and closer is going to increase, right? Because you're getting closer and closer. So the acceleration is going to increase, and the speed is going to increase, right? And it's increasing more and more this time, right? So here it says their answer was the speed of the moving charge increases since it's accelerating. It's like, well, does acceleration always mean increasing speed? And since we're in the direction of motion, right? So basically, the force is in the direction of motion, and so it's an increase. That's linking back to the idea of like negative acceleration. It doesn't always mean slowing down, right? A negative acceleration, if you're already going in the negative direction, actually means speeding up. That's what that little thing was about. And then the electric potential energy of the moving charge. What's happening to that? Well, it's decreasing as well, right? Energy's coming out of that system, going to kinetic, right? So what's happening here, though, is it's becoming a larger and larger negative number. So it's a little weird, right? And the kinetic energy of the moving charge, of course, is increasing as well. So in both cases, they're being allowed to move under electric force, and so both are converting electric potential energy to kinetic energy. So it makes sense that both electric potential energies potential energies are decreasing because they're converting to the other form. But just be careful not to be confused by the fact that the electric force is increasing in one case and decreasing in the other. Like, just because those are opposites doesn't mean everything else is opposite. It's kind of the moral of the story for those questions. All right, so that is your introduction to your lesson about motion of particles and electric fields. You've got your practice assignment here, and if you have any questions, don't hesitate to either email me or post in the post help thing or whatever. Okay. All right. Thank you for watching.